Okay, all right. A very good afternoon, everyone, and good morning to in whichever regions that you are from. Thank you for joining us for this technical webinar session. And the topic that we're going to be talking about today is the current trends and development of V2X, Vehicle to Everything, and also the intelligent transport system. So we are lucky to have a very well-renowned two speakers for this afternoon. By the way, this event is actually co-organized by the IEEE ComSoc Sri Lanka chapter and the IEEE Malaysia Communication Society and Vehicular Technology Society, or ComSoc VTS joint chapter. And this is actually part of the program in IEEE ComSoc called the Sister Chapter Programs. So we have decided to collaborate between the IEEE ComSoc Sri Lanka and also IEEE Malaysia. So before we go on, let me just do some housekeeping. Right? Basically, for this event, there will be two sessions. The first speaker will be Dr. Rudzidatul from UTM. She will talk for about 45 minutes, and the topic will be on V2X, especially the trend and also the current standard being utilized in Malaysia. And then after that, we will pass over to the second speaker, Mr. Thusitha Parakrama from, actually, he's originally from Sri Lanka, but currently working in Germany. So he will be talking on the intelligent transport system for 45 minutes. And after that, we will open up the session for Q&A. So if you do have any questions, you can either type in the chat box, or you can also raise your hand and I will allow you to actually talk. We hope that everybody can mute your microphone. If you don't mute, and I will mute you. And then because we hope that the flow will be smooth throughout the 2-hour session, hopefully that we will be ongoing. And then if you can also switch off your video because in order to optimize our bandwidth for the certain users. So we hope that only the speakers will be switching on the video. Even I will switch on my video later on as well. So without any further ado, let me introduce the first speaker. So the first speaker will be Associate Professor Dr. Rudzidatul Akmam from Universiti Teknologi Malaysia. She is currently the chair for the V2X Subworking Group of Malaysian Technical Standard Forum Berhad, MTSFB. So a little bit about Dr. Ruzi. So we call her in short Dr. Ruzi. So Dr. Ruzi is an associate professor at Faculty of Artificial Intelligence, Universiti Teknologi Malaysia, and a fellow at Wireless Communication Center. So she also served as the Ubiquitous Broadband Access Network, or U-band research group in her faculty as a research member. She chaired several international conferences, namely the International Conference on Telematic and Future Generation Networks, International Conference on Smart Sensor and Applications, and her national contribution is significant as she becomes the chair of Vehicle to Everything, or V2X Subworking Group under the Malaysian Technical Standard Forum Berhad, and leads in deliberating the V2X Technical Code for Malaysia that will be published soon. So she also served as the International Future and Networks IFN Working Group as a member from 2019. So she has been collaborating a lot with other universities as well, especially Indonesia, Greece, Germany, and the United Kingdom. So I think her biodata is a bit longer. You can also read in the emails that I've sent out. So I won't talk too much on the background because I think we would like to hear from Dr. Ruzi herself. So the floor is yours, Dr. Ruzi.
All right. Thank you, Prof. Yusof, as the chair of IEEE Malaysia chapter. So let me share my screen. Okay. Okay. Wait. check if I can use a pointer. Okay, all right. Okay. Very good evening and very good morning to all the participants. So I'm Ruzi. You can call me Ruzi. So I'm going to present on vehicle to everything for in terms of system architecture, specifications, and research. So Prof. Yusuf has introduced me, so I don't have to introduce myself again. So what I'm going to talk today is I will introduce you about the technical code. So basically, Malaysia has deliberated a technical code on V2X since last year. So finally, we have come out with the technical code, and it is in the process of final review by the regulatory in Malaysia, which is MCMC. So I will introduce you the technical code and the scope and references and the objective of the technical code, the requirements, and I will conclude the technical code. And at the end, I will share with you some practical research works under Wireless Communication Center. So now the idea of introducing you the technical code is actually to promote the TC. So once it's published, so I hope all the researchers, whether in Malaysia or in Sri Lanka, you can refer to our technical code for your research works or maybe for the development of V2X or autonomous vehicles. So before I begin, let me share with you the structure of working group. So we have several working groups under Malaysia Technical Standards Forum Berhad, and this MTSFB is actually subsidiary of MCMC. MCMC is a regulatory bodies in Malaysia. So this vehicle to everything V2X sub working group is actually under IMT, International Mobile Telecommunication and Future Networks. So we also have number of sub-working groups, crowdsourced applications, IMT 2020, and also Volte. This is a new one. So all these sub-working groups have deliberated their own technical codes. Okay. This is the structure or the leaders, IMT and Future Networks group leaders. So we call IFN, the short form, the abbreviation, leads by, so the IFN working group leads by Mr. Rakuram Gandhi from Maxis. So Maxis is one of network operators in Malaysia. So he's the chair of IFN working group, and the vice chair is Mr. Anwar Faiz from Telecom Malaysia Technology Services. And the secretary of IFN working group is Dr. Bruce from UTM. So we also have a secretariat of MTSB who is actually Mr. Ikhwan, who has been helping us in terms of how we're supposed to write the technical code, as well as how we're going to, the process of publishing, writing of the technical code. So Mr. Ikhwan has helped us a lot in terms of this. So this is the structure of the V2X sub-working group, which is under IFN working group. So of course, I am the leader. I am lead the V2X sub-working group, and the vice chair is Mr. Yo from Telecom R&D, Research and Development. And for the secretary of V2X sub-working group is IRTS Dr. Muhammad Zamri. So what is actually covered in our technical code? I will say TC, the abbreviation. So the V2X technical code actually specifies the system architecture and specifications for V2X over cellular networks. For your information, there are a number of V2X communication technologies like the SRC or IEEE 802.11b. But for this technical code, we concentrated on cellular V2X or CV2X, which actually focus on the 5G. Now, the idea why we focus on the 5G, because as you know, the 5G can be successful when we have number of verticals or use cases. So that's why we emphasize the 5G V2X in this our technical code, so that Malaysia can have many verticals, many verticals, many 5G use cases that can make the 5G become successful in Malaysia. So these are the references. So mainly we will focus on the, because we have number of technical codes here in published previously. So our main reference, of course, the previous technical code, and also the ITU documents and the 3GPP documents, and can be IEEE documents. So all these official references are our main references, I would say. Okay. So now the objective of the TC is to develop the TC that specifies, of course, the system architecture and technologies for V2X over 5G. And at the same time, this TC will support the standard developed by the Department of Standards Malaysia. So Department of Standard Malaysia has actually come out with a standard part 1, which is called next generation vehicle. So they are still preparing or drafting the part 2 standard, the NGV we call it, the acronym, NGV part 2 standard. So we hope that our TC could actually support the standard that is developed by Department of Standards Malaysia. So in our TC, okay, there's a delay. Wait a minute, yeah. So in our TC, we cover the overview on V2X. We will see next the V2X requirements, the V2X communication architecture, as well as at the end, we concluded with some potential V2X scenarios that we can develop in Malaysia. So these are the 4 types of V2X. I believe most of you know about this here. So there are 4 types of V2X. Which are actually V2V, as you can see here. So the name V2V, meaning that the vehicles communicate with the other vehicles. So this is vehicle to V2V communication. Another type is V2P, vehicle to pedestrian. So the vehicle communicate with the pedestrian. But some documents, they refer the V2P as V2D, vehicle to a device. So the device is actually attached to a pedestrian. So that's why somehow this device is used for the monitoring, maybe for tracking or to send an alert. So that's why we actually categorize V2D as V2P as well. But some documents actually distinguish these 2 terms. But in our TC, we decided, because we refer to the 3GPP, so we decided to use one classification, which is V2P, that is actually comprises of V2D as well. So another type is vehicle to infrastructure. So you can see the vehicle to infrastructure is more on the vehicle communicate to the roadside units. So for the V2X to be developed or to be implemented, so we need to have radio site units by the roadsides, or we call RSU. So when the vehicle communicate to the radio site units, this is called V2I. On the other hand, when the vehicle talk to the base station, and then to the V2X, to the 5G core, of course, and then to the application server. So this is known as vehicle to network, or V2N. So these are some applications that we categorize as vehicle to vehicle. So this is for V2V warning propagation. For instance, when we have accidents at the front, so the vehicle with the vehicle facing the traffic accident will send an alert or a warning to the vehicles at the back. So this is a rearward propagation or V2V warning propagation. Now, another type of forward propagation, for instance, when we have ambulance at the back, you know, sometimes we only hear the sirens or the sound. Okay, so it will send the first car or maybe the ambulance, the car that is near to the ambulance will send an alert or a warning to the other vehicles for the vehicles at the front. Yeah, so this is called forward propagation. So another type of vehicle-to-vehicle applications is vehicle-to-vehicle platoon communication. This is more on like a convoy, yeah, a convoy of vehicles. So we have a convoy of vehicles. There's a leader at the front who leads all the vehicles together. So this one, it will navigate a group of vehicles at the back. So this, of course, hope that with this V2V platoon communication, it can contribute to the safety and to improve the traffic flow. And some people say that it can also contribute in terms of fuel consumption. Now, the other case for V2V beckoning, so we will see afterwards in the last in my last slides on a case of V2V beckoning. Yeah, you will see afterwards. So now let's move on to vehicle to infrastructure applications. So this is a case of V2I here, vehicle talk to radio site unit. So, and then another one, vehicle to network applications. I have actually explained this, where the vehicle communicate to the base station and can goes up to the application server. For instance, when it comes to diagnostic, we want to diagnose vehicle diagnostic. This is a very good examples. Basically, by having the vehicle's profile in the vehicle diagnostic server, for instance, then we don't, when you go to the mechanics or to the workshops for maintenance or maybe to change the fuel, the oil fuel here. So basically, this one can accommodate, it doesn't need to be manual, but it will have a history or a record of the maintenance for this one, for the vehicle diagnostic. So this is an example of vehicle to network applications. So for V2D, as I mentioned, when we have a pedestrian crossing the road, so it has a device, so it can send an alert. So this is a type of V2P scenario. So now for V2X requirements in the TC, we emphasize more on the cellular V2X. So we give the overview of V2X that work in 5G networks. As you can see in A, this is standalone. So the vehicle communicate to the G not B through the 5G and then towards the connect to the 5G core. Okay, so the vehicle communicate to G node B via UU interface, but when the vehicles communicate with other vehicles, with the downstream vehicles, it will go through the PC5 interface. So this is an example. This is the overview of V2X, how it works in standalone. At the same time, the V2X can also work in non-standalone. So the difference here is that you can see for non-standalones, for the radio access networks, it comprises two. It has 5G here, G.B, as well as the E.B here for the 4G. So this is dual connectivity. So, but the difference is that the core is still LTE core, is still EPC, Evolved Packet Core and switch here. So this is the difference between the standalone and non-standalone. Non-standalone still ride on the, still anchor on the EPC, on the LTE core network. So then we cover the overall requirements. There are some requirements. You already know how the networks works, the types. So in order for the V2X application work successfully, there are overall requirements for each network elements. So we highlighted in terms of user equipments. So the user equipments here is the vehicle. So the vehicle must be pre-configured by the 3GPP network. So that is a must. So it's sort of the vehicle will have its own vehicle ID. So there are a few more requirements, but I don't put it here. You can see the TC once it is published, the details. Another one is the radio site unit. The requirements that for the radio site unit, it can serve up to 200 UEs. UEs is the vehicles. So it's quite a lot if it's 200. Quite a lot, yeah, if we have a number of radio sites unit. And then we have the transport for the message transfer prioritizations, because we will have number of applications as I gave you some examples just now. So basically the transport can prioritize the applications of V2X. So besides that, it also determine the transmission rate, also the charging. So for the 5G, this one, it's more on the communication between the UE and application server in terms of the security, radio resources, and also communication optimization. So basically, the standards have defined all the requirements. So now we go in depth, in details, the specific V2X service requirements. So basically in the standard, it has specified the latency, message size, message transfer frequency, range requirements, speed requirements, and also the speed requirements. So this is the latency. What you can see is that for V2V and V2P, for non-critical applications, it requires 100 milliseconds. On the other hand, for critical safety applications like pre-crash sensing, this one requires very low latency, about 20 milliseconds. And then for V2I, about 100. When the vehicle needs to transfer message between a UE and also with the RSU. And for networks, yeah, it makes sense. Why is it 1000 millisecond? As you can see that the vehicles transfer the messages up to the data network, to the core network here, to the application server. So it makes sense why the latency is up to 1000 millisecond. So the message size, this one spell out about the size of the payloads, yeah, 50 to 300 bytes for periodic broadcast messages. For event triggered, this one 1200 bytes. And then the message transfer frequency, so all must support at least, should be able to support 10 messages per second. The range requirements, so the range requirements is about the response time when the vehicle responds to a certain incident. So for these range requirements, 4 seconds for non-critical V2X applications. So for the speed requirements, so if let's say the vehicle has a certain speed, and the opposite vehicles has another speed. But for this one, the relative velocity. So let's say one vehicle has a speed of 250, another vehicle opposite direction has another 250. This will give the relative velocity of 500 kilometer. So what I wanted to say is that if the vehicles move at 250, it should be capable to transfer the messages. Okay, should be capable to transfer the messages, shouldn't be dropped. So if it's beyond that, so I don't know what vehicles can be go up to 250. Maybe it's BMW or Mercedes, they are very high speed cars, but normally we just drive 120 or 110 in Malaysia. So basically, with this, it should be capable to transfer the messages. We shouldn't have any drop disconnect for this speed, yeah, if in Malaysia, 110 kilometer per hour. So this about the security. I don't, in our TC, we don't really cover in details about the security because the security part has its own standard. So it's very, very detailed. So we only cover we summarize the security in terms of the authorization, pre-authorization, integrity, and confidentiality. So we hope that another working group on the security, they can come out with the V2X security, yeah, a technical code. So it's a separate technical code. We hope that the security working group can do this. Okay, so now we move on to V2X service requirements. Just now you can see the network requirements. So for the service requirements, the details, actually the 3GPP categorize the V2X scenarios into 4. Vehicles platooning, advanced driving, extended sensors where the V2X rely not in the vehicles, yeah, the vehicles in-house sensors, in-built sensors, the vehicles. But this time around, the extended sensors mean the V2X rely on sensors from the infrastructure, from the traffic lights, from the external environment. So that is actually extended sensors. Remote driving means autonomous driving. So they have actually highlighted the performance in terms of transmission rate, maximum latency, reliability. We will see afterwards, data rate, and minimum communication range. Now, this is very, very important when you actually develop the V2X applications or others applications. You can refer to the millisecond to quantify how good your ADAS system is, or maybe your cooperative vehicles communication is. So they actually in 3GPP, it has actually defined the latency. For instance, here for vehicle patterning, information exchange between the vehicles in order to support V2X applications, they have number of degree automation. Yeah, they have L0 up to L5. L5 means the level of automation is full automation. So in fact, they have categorized the degree. So you can look at it at these service requirements. So this is for advanced driving. Yeah, why there are more. There are more scenarios on advanced driving, but I share you some. Okay, some information sharing, but you can see that the latency required for the information sharing between the vehicles is quite low, only 100 millisecond. They don't really define the data rate, but they define the reliability, yeah, for a higher degree. So this is for advanced driving. For the extended sensors, as I've mentioned to you, meaning that the V2X rely on the sensors from the external environments. So for this one, it's very critical. As you can see, for the higher degree of automation, it requires up to 3 milliseconds. So this can be only implemented when we have 5G standalone. Yeah, with 5G NSA is very, very impossible. So look at the reliability is very high, 99.99, and in fact the data rate are defined, yeah, for the extended sensors, because this is very important when it comes to critical applications. So we rely on the extended sensors. So that's why they spell out the data rate and also the reliability. That's the reason. So now for the remote driving, now how is it to implement the remote driving? It requires 5 millisecond latency. So if let's say our network can't accommodate or can't support with 5 millisecond latency, it's impossible to have remote driving. And the reliability is very high, 99.999, which is can only be supported by 5G standalone. So this is more detail about the architecture, those who wanted to know the architecture. So we have the UE, the vehicle. So we have the application. As I mentioned, the UE communicate with other UE or the vehicles there. Communicate with the other vehicles through PC5 interface. And then this is through the RAN, Next Generation Radio Access Networks. And then through the 5G core, where we have a few functions here. The UPF, user plane functions. From the user plane function, as we know, the 5G separate the control plane and user plane. So the user plane handles the user data messages. So that's why it connects to the data network and also V2X application. server. So now, let's say if we have roaming means that we have this V2X application and you are attached to visiting public land mobile network. So basically, there are two types. If it in case of roaming, there is a local breakout. Local breakouts means the the visiting network operator actually direct the data messages to its own data network and V2 application server. On the other hand, for home routed scenario, the difference is that the UPF and the VPLMN communicate with the home. The home public land mobile network, and then it can access the applications, the V2X applications only through the home public land mobile networks. That's why it's called home routed scenario. So this is our two cases. Okay, which one? It depends on the network operators. But of course, for the local breakout, it needs agreement, yeah, between two network operators, for instance. So this is a V2X communication architecture. So there are two modes. So if let's say you are in the coverage where you have the 5G, so we have direct communications, the Sidelink PC5, and also UU interface. So this is in case there is a coverage of 5G. So let's say you are in a tunnel, don't worry about that. You can still enjoy the V2X application. So in case there is no coverage, we will have sidelink, meaning that the vehicles will communicate with other vehicles through PC5 interface. So then there can be hop, yeah, in case if let's say the tunnel is very long, so it can be hop from one vehicle to other vehicles up until we have the coverage, then can access, the vehicle can access the server, for instance, for certain applications. So in the TC, we also cover more details about the architecture, on the provisioning, on the interworking, the user plane. As I mentioned just now, there's direct communication, the side link where we have the PC5 interface. So we actually highlighted on the user plane protocol stack, the control plane protocol stacks, as well as the PC5 signaling protocol stacks. So we also discussed the service provisioning. Yeah, as I mentioned just now, the UE must be provisioned first. Okay, so then we highlighted the V2X communication provisioning. The most important thing is about the frequency. So for direct communication for the PC5, the frequency required is 5.9 gigahertz. And we also discussed the V2X for the 5G V2X operating band. But this one we refer to Malaysia regulatory bodies, MCMC. Yeah? So we get the inputs from them. What type or what are the available spectrums that we can use or implement for our for V2X in Malaysia. So we actually concluded the TC quite nice, where we have V2X, some potential V2X use cases. This one, we get the inputs from our automotive manufacturer, Proton, Perodua, and also who actually provide the AV test beds. So we sit down together with Mari. So this is led by Mr. Farhan from Malaysia Institute on the Automotive and Internet of Things. So we sit down together and discuss the potential use cases. Some of these use cases already implemented in Malaysia, but of course they are not using 5G. They are using LTE, for instance. Yeah. So for V2V, you can see a few use cases here. I don't really go into details. We can see parking management. We can see real-time vehicle diagnostics, yeah, firmware, software updates, traffic updates. This one more on the updates that because of course the vehicles have some software, it needs to be updated. So all this falls under V2N. Okay. So the conclusion, as you can see, our TC has successfully specified the underlying system architecture for the V2X over cellular networks, or CV2X. We focus on the 5G, as you can see. And we really hope that the TC will be used as a reference to the Department of Standard Malaysia, where they will develop the next generation vehicle standard part 2 in Malaysia. So with the TC, actually can reinforce the future national plans such as the road infrastructure, the mobile networks, and also the facilities for V2X. Okay, so I would like to acknowledge. So this has been done with a very good team. So these are the industries or the agencies, the universities who have been who have actually developed the TC together. Okay, so all these I would like to acknowledge all of them. Maybe they are here, maybe they are not, but these are the groups that have been developing the TC. So how much time I have, Prof. Yusuf?
Uh, around 5 minutes.
5 minutes. Okay, I make it quick. Okay, for the research works, so very quick one. Okay, this research works actually under the Wireless Communication Center. Now, once actually this motivates me and a team. Once we developed the TC, we were wondering, okay, why not we measure or quantify the current 5G in Malaysia? So we have conducted a 5G drive test experiment in Kuala Lumpur to see how we can accommodate. As you can see, there are a number of categories just now. Player tuning, extended sensors, remote driving. Another one is what I cannot remember. So all the four, they have actually spelled out the latency, the data rate, and the reliability and the range. Yeah. So this one has been done by Ryan Ramos. Yeah. He was an intern from EdTech Malacca. So I should thank him for this, and also with the support from Arsani. Okay, so basically we know V2X rely on a 5G. Okay, so I already talked to you about the motivation. So basically we can see from the previous works from like China, Finland, even from TUC in Germany, they have investigated the 5G performance, yeah, but more on the test bed. They use their test bed. And some of them just reported, okay, this is the latency, this is the data rate, but they don't really check whether the current performance can accommodate their service requirements as specified in the 3GPP standards. So this is what we have been doing. Okay, so there is a lacking in terms of that. Except for TUC, they have done this, but they don't really refer to the current 3GPP standard, where we actually refer to release 17. Yeah, TS 22.186 release 17. So let's make it quick. So basically, we have conducted drive tests from Pahang Roundabout in Kuala Lumpur, the capital of Malaysia. So it's round trip drive test morning. We have conducted twice, morning and evening during weekends. Of course, not during weekdays because it's very high traffic. So, but during weekends also have quite high traffic, but not as high as during weekdays. So the speed of the car moved about 24 kilometers per hour to 45, and it was sunny weather. Okay. And then we also conducted another area. We actually conducted the test at a very high traffic. So drive test from Ampang Point to Renaissance Hotels. Okay. So these are the tools that we use. Actually, we tested 3 tools, drive test tools. We try GNet Track Pro, we try Ookla, we try Open Signals, and then we study which is the best. So you can see GNet Pro on your left side, the interface. So we installed the apps, yeah, mobile apps in our phone, and then the Ookla Speeds on your right side. So now, actually, after we have compared the drive test tools, we decided to use GNet Track, because GNet Track Pro has many features, very good. to study, to measure the networks. Very good. To have maybe like machine learning to study performance, very, very good one. But you need to pay 60 ringgit Malaysia to have a GNet Track Pro. I should thank Professor Dr. Fizi for this because she recommended me this drive test tool. Okay, so but however, we found there is some, in terms of latency, it's very, very high. So that's why we try Okla. So and then we try open signals, yeah, to look at to study which one makes sense in terms of the latency, so that we can compare which is the best tools to use. So out of the three tools, only GNet Pro has reference signal receive power, RSRP. So you can see that during the morning time, the RSRP about 70 to 80, so very good. But in the afternoon, maybe after lunch, yeah, during weekends, so everybody like come out, there are so many cars on the road, so that's why the RSRP is it's not that good actually. It's 180, negative 80 to negative 110 dBm. Okay, so you can see this is the average. RSRP. Okay. Maybe I should go. Okay, so about the Okla speed test, you can see that they have similar. So we compare Okla and GNet Track Flow. They have similar CDF trends for both tools because they
Sorry,
converge
Dr. Lucy.
between, yeah?
We cannot see anything.
Ah, really? Okay.
Uh,
So I should share again.
yeah.
Okay, let me slideshow first. Okay. Can you see now? Oh no.
Okay.
Okay. So this one, they have similar trends, yeah. Both converge at 4.2 and 4.4 megabits per second. Okay, so and then, however, when you look at the latency, yeah, when you look at the latency, the GNet Track Pro, we have done this many times. It seems that GNet Track Pro doesn't have very good latency. So with several discussions with colleagues, maybe because of the server is very far away, so that's why it caused very high latency. We have done many times and we still get similar results. But Okla quite good. Yeah, it makes sense because we actually compare Okla with open signals. They have quite similar latency. So that's why at the end we decided to use Okla for certain reasons, yeah, to actually do the measurements. So this one makes sense for the latency. So at the end, after we have done these measurements, yeah, for these two different locations in Kuala Lumpur, capital of Malaysia, and then we map to remember just now the 3GBP service requirements? Yeah, so we map to the four use cases, but there are a number of scenarios for each use case. So what we conclude is that for the current 5G in Malaysia, it can only accommodate more on the information sharing. Yeah. So because it has very low latency, because the latency is about 20 millisecond to 25, can be 50, 20 to 50 millisecond. So with such latency, Malaysia can only support information sharing between the vehicles, maybe the vehicle with the radio site units. But when it comes to data rate, no, it's very poor. Okay, we tried this many times, and maybe because it's mobile, yeah, mobility. So that's the reason why. So this is the conclusion for our first project. Now, very quick one. This is another project, fleet management. So this is more on the bus monitoring and tracking. This project is funded by Asian IVO and it's led by Prof. Sharul Kamal and her team. So this one involved several with number of universities, yeah, from Singapore, Brunei, Indonesia. So they have actually implemented the test bed in Malaysia and also in Indonesia, in Surabaya, for this, what you will see next, yeah, the test bed. So in Johor deployment, so they have again selected two areas, P411
Sorry,
from
Dr.
Hyundai.
Rosie. You have 1 more minute only.
Okay, okay.
Hope you
So
can wrap up.
yeah. So this is 31 stops with one bus and 26 stops with two buses. Okay. So from there, so this is the setup at the vehicle. We have the data card reader, we have the Wi-Fi access. So it's actually we install the beacon in the. That's why there is a beacon where in the bus so that it can send an update of the coordinates, the location through the bus stop. So the bus stop we install a Pi 3 to actually transfer the data received from the bus to the cloud. Okay, so this is the setup. You can see, so we have for this one use 3G connectivity or can use 4G, and the purpose of this project is actually to predict the bus, the ETA, the estimated time arrival for the buses. So for the prediction, we use data analytics and prediction. We use machine learning to predict so that the user can know through the mobile apps, they know when the bus will come to their destination, yeah, to their bus stop. So this is the antenna in transportation system. So this is where we use vehicle beaconing for this project. So this is the dashboard, yeah, and this is the dashboard again. So if you have any inquiries about regarding the report just now for the ETA or the bus monitoring and tracking and the estimated time arrival, you can refer to Prof. Sharul, yeah, because he's the leader. So with that, okay, Prof. Yusuf, I hope I'm in time. Thank you. So maybe, yeah, thank you, Prof. Yusuf. Back to you.
Okay, thank you, Dr. Rosie. Yeah, we are about we are in time, right? There are a few questions in the chat box, but we will answer that at the end of the session. Yeah,
Okay.
Dr. Rosie. Maybe you can have a look at the question first, and then
Okay.
prepare the answers for later on. All right. So thank you so much, Dr. Ruzi, for the first session. Our next speaker is quite far from us, Mr. Thusitha Parakrama. He's the head of department at Hyundai MOBIs Research Center in Europe. So he's currently in Germany. Okay. All right. So before I hand over to Mr. Thusitha, let me just read a little bit of his background. His bachelor degree in electrical engineering is from University of Moratuwa, and then his master in information and automation engineering from University of Bremen, Germany. Then he was a researcher at Institute of Cognitive Neuroinformatics, also at University of Bremen. And then later on, he became the head of the department at Hyundai MOBIS Technical Center in Frankfurt, Germany. So Mr. Thusitha is a well-known professional in the advanced driver assistance systems, or in short, it's called ADAS industry. With more than 20 years of experience, he's been a key player at prestigious companies like Bosch in Germany and Hyundai MOBIS Technical Center in Frankfurt. Currently, he's leading the system development department for ADAS at Hyundai MOBIS Technical Center in Frankfurt. His academic pursuits include research in cognitive robotics, vision, and significant contribution to conferences and IEEE recognized papers, highlighting his commitment to advancing automotive ADAS technology. So without any further ado, I'll pass the session to Mr. Thusitha. So the Windows is yours, Mr. Thusitha.
All right. So I hope you see the slides on the panel.
Yeah, we
okay.
can see the
Yes,
slides.
thank you, Professor Yusuf. to introducing myself to the audience. I'm very glad that the invitation, I accept that. So I will just go through some of the research that we did in recently, mainly in our Frankfurt Center, and also what we did in so far in the advanced driver assistance systems and advanced parking sector. Let me introduce a little bit what we go, and then you can get a better understanding what MOBIs is doing. And then first I jump into mainly the what is ADAS for the people who is new to this sector. And then I jump into some of the research that and some of the products we developed in ADAS. So the MOBIs is a tier one company, automotive tier one company. And then we have several sectors in autonomous sector, connectivity and electrification. So we develop almost all automotive sensor technologies and parts, the mainly ADAS sensors, IVI, that means HMI interfaces, electrification, electrical drives for electrical vehicles, the braking systems, steering, suspension, safety, lamps and modules, and other accessories. So we are not only producing for Hyundai and Kia Motors, but we are producing for the world. Actually, we have a lot of other customers all around the world. As a normal tier one company, we supply all of them. So let's move into the my agenda today. So the few points I need to highlight in this talk, mainly the understanding the ADAS and ADAS sensor clusters, mainly what we use, and ADAS software development, what quite challenging part, and then for the young professionals who needs to come into this sector, carefully listen this, that part is how the software is evolved, and then what is the expectation in future. And MOBIS advanced parking assist, what we did recently, and challenges of autonomous driving software. These are the areas that I mainly need to talk about in this today. Let's move into why we need ADAS. Actually, you may never heard about perhaps that's the dangerous species around is actually the car, the driver. 1.3 million fatalities per year due to car accidents. So that's a huge pressure for the car manufacturers like us and the researchers. Please get down to the safety and standards and stick into the safety and assure the safety of the driver. And this mainly due to the human errors. That's why we need the automation to assist the human. At the same time, get the full automated if possible. And mainly the insurance and other companies is struggling to meet these targets, at least half the fatalities in near future, at least as soon as possible. So get into the mainly the ADAS safety. So there are several levels of ADAS safety. For example, the quality management, this is we call QM, GPS, navigation systems, satellite and radio communications, and USB and HDMI connections. And these are lowest level of safety. It doesn't matter if that fails, it still you can run the vehicle. And ASIL A, that means automated safety and integrity level A, is still not the lowest. It's another level that we need to reach. For example, rear lights, heating and cooling system, body controls unit, but still need some safety. ASIL B is the brake lights, rear view cameras, instrument cluster, and ADAS. I look at, you can see that ADAS is still in ASIL B level. That is not even in the highest level, but the target is to get into the highest level. The ASIL C systems, you can see ADAS, some part of ADAS still in ASIL C, and battery management and suspension. You can see that in one of these failures, it's caused you have to stop somewhere. And coming into the ASIL D, the airbags, anti-lock braking system, electrical power steering, power drives, and these are ASIL D level. So one of these breaks, it causes a lot of fatalities to the living beings as well as to the assets. So ADAS still need a big journey. So we are still in ASIL A level or either in ASIL B level. The target or the request from the audience, from the public is please move into the ASIL C and D, and then we need better sensors and also the software. And then both sectors, not only the hardware, we have to meet the software safety as well. So that that is the challenge that I need to put it in the first, and then I will move into the next. So before getting into the autonomous levels that what is requesting currently, there are several levels of automations. Still in ADAS level, we have level 1. You need the full driver assistant for that. I mean, full driver attention for that. Its system assists you, but system doesn't controls you, and the driver needs full attention. The level 2 autonomous driving or automation needs partial automation. So driver get the some of the supports from the system, and then, for example, object detection and emergency brake even could do, but still the driver needs the attention for the full system, and then he is responsible to get the safety and then look at the vehicle and the road and so on. And level 3 autonomous driving or automation is a conditional automation. Then you can hands off. Actually, a hands off means you can hands off from the steering wheel, and you have still the level 2 autonomous part is there. That means brake is also brake pedal. You can feed off from the brake pedal, and then you can drive. But still, human driver is as a backup to any time to interact with the system and stop the vehicle. So feet off, handoffs, you can understand that, level 2 and level 3. Then level 4 is the highest level that we could achieve at this stage. Is level 4 is the eyes off, the complete eyes off from the system, and the full system get the full control during the driving, but however, attention needed. So it's giving the attention, but it's not allowed to sleep the driver. But the level 5, I don't want to talk much on that. So I stop in the level 4, and you can see that how advanced the systems are at the moment, and then how to achieve this kind of safety is the next goal. Let's move into the ADAS sensor clusters. What are the sensors that frequently used in order to achieve such automation? There are few sensors, not many actually. So still the smart front camera is one sensor. So you have a camera in front of your steering wheel. I mean, in the upper middle of the windscreen. So that can detect up to 120 meters maximum. But you have an opening angle of 120 degrees, and then you can detect certain objects on the road, also as the outside the road. That is the primary sensor. And surround view camera, that actually you can detect not much far away, actually 1 meter to 30 meter detection for parking mainly. It is surround view, that means you can cover 360-degree coverage around the vehicle by 4 cameras. The front camera is usually a single camera, and then you get 360-degree 4 cameras from surround view cameras. And then you have ultrasonic sensors. Ultrasonic sensors is only for very short range detection, up to 5 meters maximum. And then we have the developed sensor already up to 7 meters. But these are the range that is mainly assisting parking. So this the surround view camera is also assisting for parking. The front camera is assisting mainly for driving, not for parking. And then coming the radar sensor technology. The radar sensor can detect 220 or 300 range, and then several different radar sensors, long range, medium range, and short range for different applications. And the system designer can look at what is the application, what is the safety level they want to achieve for a certain vehicle platform, and they can look at these sensors. These 4 sensors are mostly in the market currently, and it's heavily used currently in most of the system. In ADAS level 1, level 0, level 1, level 2 systems, you can see all these sensors in the right side. We'll jump into the left side. So Lanka is another sensor that came up with very good point clouds. I mean, you have many points, not like camera, but still lower than camera, but you have very good resolution. It can detect 200 meters, and then, but it's a very expensive sensor as compared to all sensors what we look at in the right side, and the LiDAR sensor is most expensive. Therefore, it is not frequently used, and even it's a sophisticated sensor, but cannot afford if you put it into the system. And then there's another sensor that look at the driver's monitoring and driver's conditions. That is driver monitoring, and it is a purely interior camera, and then it is not particularly assisting for driver, but however, however, it is not particularly assisting for driving, but however, to wake up the driver and giving alarm and signals, it is necessary for example, level 1, level 2, and level 3. There's all of these levels of automation. Driver attention is needed. In case the driver attention is not anymore, and then it's giving the right signal to the driver, please wake up and take the control. It's connected with other systems as well. And then the new sensor came up recently, that is the thermal camera sensors. Actually, you can detect any living being with the thermal temperatures. And this is thermal camera. Thermal camera, as you know, it's very expensive sensors, and all around the world you cannot afford. But for the automotive, currently is developing for very cheap sensors that could do the job and then detect particularly very good resolution in 150-meter range. So that will come into the market very soon, and that particularly assisting for level 3 and so on. So these are the sensors mainly. And then in terms of the resolution point of view, camera is still the best sensor and cheapest sensor, all of them. And then the radar is the next sensor that's most popular and also well established in quite nearly 10 to 20 years been in the market, and no more actually, no more much errors, and then it is very reliable in terms of the operation. Then I will give the timeline how that could evolve in the next generations. Mainly the level 1 is currently looking at with the radar sensor, mainly camera sensor, front camera, and there's no LiDAR. So level 1 we could achieve with that. Level 1 systems already in the market from even 2008 and 2015. The level 2 in the market, that you can have radar, more radar sensors, 3 to 5 radar sensors in the system, camera, more than 4 cameras, front cameras, and 4 surround view cameras, these yellow balloons. And then together we can have full 360-degree field of view of the vehicle, and at the same time giving the better field of view in the front. And still you have front radar to front object detection, and then other radar for corner radars for corner object detection, blind spot detection, and so on. And still we don't need the LiDAR. And level 2 is currently developing level 2 plus, level 2 plus plus, and so on. But still there's no LiDAR sensor. It's needed. It's a 0 to 1. It is actually optional. You can see that the automotive industry is looking at cheaper sensors and bigger safety, not to afford large sensor clusters in the vehicle and achieve the maximum safety. It doesn't work because of the total system cost will enormously high if you add more and more sensors, and in terms of the sensor management and point of view. We are looking at level 3 to 5. Level 3 is 2026 timeframe to be in the market, but still in some automotive companies already in the market, in particular countries only, but in the worldwide 2026 to 2030, level 3 and level 4 and full autonomous is the dream that everybody want to look at right now. Yeah. So I think Professor Rudzidatul has nicely explained about most of the part of the V2X and V2I and V2V. So I don't need to touch on that part. Actually, it's well explained. What are the challenges and latencies that you could see? Actually, as an automotive supplier, automotive part supplier, sensor supplier, we are looking at complete revolution in automobile industry, particularly in software. We need the complete automotive, complete automotive in full access to the like a mobile phone to everybody. That means mobile phone is on the wheel. That is the concept that we are working on. So we need everything, all the information available to the driver as fast as possible, and then process together with the existing sensor clusters. We talked about a lot in the latency and other issues with respect to V2V and V2X and so on, and in V2I. And then the sensor cluster currently working in 30 frames per second. 30 frames per second mean nearly 30 millisecond and 60 millisecond time frame. We had to compute everything. All the sensors, we receive the information, our computing unit and the software process all the sensors, and then algorithm worked out and giving the right actions to the driver. So that is the time frame. That is the the normal processing cycle for ADAS system. So any sensor that coming up outside, so we need that information within 30 millisecond to 60 millisecond. Actually, 30 millisecond is the most the required one. That means you have to finish all your computation in 30 milliseconds for all the sensors, including algorithm and sensor fusion and so on. So that's the challenge. And then that is for fast vehicle and for full autonomous driving. But still, this latency is kind of a thing that we need to achieve. In automotive has very stringent quality standards. That's why very few players around the world that could achieve automotive software and sensoric as well. I mean, the main one is the automotive SPICE, automotive software process improvement capability determination. So that is one area. Automotive SPICE has given the levels. Automotive SPICE level 1, 2, 3, and 4. Higher is the best. And now looking at automotive SPICE level 3, and even very hard to achieve even automotive SPICE level 1 in terms of the software quality. And then we had to meet ISO IEC 15504. That is another standard. It's very much resembles ASPICE. Actually, it's based on ASPICE all that we need to achieve. And then before that, any software before we release into the vehicle and integrate and then put it into the public, we had to achieve ISO 262 functional safety requirements. That is very high level of requirement. Even we had to get it into the software level and find out all the failure modes, any failure modes, how to act and how to react and how to face for the latency, how to face for the sensor failures and so on. A lot of guidelines provided to achieve in this area. And then we follow software development V model. This everybody knows from the school what it is, but however, we have to develop in the above standards. But then another one is the CMMI level. That is kind of a maturity level of your development team, whether you have experience of putting that into the market. And these are the then assets based on that. And then FMEA, failure mode effect analysis, I mentioned around ISO 26262, and then source code level and the functional level, we have to assure that any failures and then what is the fail-safe action. That's why we need more sensors and more redundancy on these sensors. As one fails, the other has to take the action, and then support for safe driving. And cybersecurity is another area that is quite related to the V2X and V2N, V2I, and then other V2V, except at the same time, we have to meet ISO 21434 compliance automotive cybersecurity. But that has a big challenge because we are planning to flash the complete software over there. Flash over there. That means software, we process it in a cloud, and then we allow the owner of the car to get the updates automatically. Even the complete algorithms and even the sensor layer drivers and other aspects as well. So we had to assure this functional flashing over there, full safety. So this is one challenging area that we are currently facing. I explained a little bit about automotive SPICE. I mean, you had already some overview about the what is automotive SPICE and how to get into that. You already know the V model of software development in your school. Any software developer already had this. So we have a system design part in the upper corner. So system design. System design has mainly two parts: system requirements and system architectural part. And then the rest is the software development with respect to the system requirements and system architecture. And then this has several layers: software requirements, software architecture, and software unit design. And then the right part of this is complete testing. Everything we had to test and then pass the test in order to go to the higher. And ultimately, to get into the system 5, the system qualification test, we need to pass all of these tests, followed by system 4, software engineering 4. That means software unit verification, integration tests, qualification tests, and then the rest. So this is strictly followed. Therefore, every block is in this ASPICE development is it's handled by domain specialists and big teams, not a single person. And then level ASPICE level 2 and 3 is like we had to maintain, for example, complete thing and complete documentation of all the softwares, all the designs properly and maintain, and then we have to follow these guidelines. So that is another area in the ADAS software development. As I mentioned, there are so many sensors coming into the market. So we are looking at the system development, the sensor in the system level. But however, coming into the software is getting much bigger complexity every day. So more sensors, more safety mean more complexity. Actually, that's why the productivity of ADAS at the moment is getting much lower rate than actually the complexity of the software is getting very high. So therefore, it's already identified by the industry because large modules and then becoming increasing complex because of the so many algorithms and some other interaction with other sensors and other control units in the vehicle. So that all together ADAS is much more complex system. You can see that still I'm talking about advanced driver assistance system. You can think about that autonomous driving is much more complex. Okay, so that is the overview of the ADAS industry. That I will jump into one application that we developed. Mainly one sector of MOBIs is the MOBIs parking. That's what I'm currently involved in. I will give a full overview and what is the current trends and what are the sensors we use and how is the future will be. So parking has a lot of requests because parking is a stressful function in everybody's asking whether you have autonomous parking because parking spaces are getting smaller and then much more challenges in parking areas and find out the parking, even at home parking as well. So this is the main areas that why the parking is kind of a thing that we mostly focus currently and as soon as possible to get into the market with some advancements. So the parking has some accidents because of the pedal misapplication, risk of collision into nearby objects or living beings, and parking at busy areas is quite stressful, and waiting times and also leaving the parking garage at busy area and small, and then also the heavy traffic obscure the sign and making driving parking even more difficult. And then another big factor is narrow spaces and how to handle narrow spaces, how to look at that and the risk of collision. And these are the near distance sensors that I mentioned before, like ultrasonic sensors and near range parking cameras could potentially give a better support for the driver. And most of the parking areas with a lot of other boards and signs, it's confusing. That's why the autonomous parking is a key for the next generation. So these are the two main authorities actually currently looking at and give the certification of how your system is capable, mainly with respect to the parking, not only parking, driving as well. For example, Euro NCAP, they test your system before getting to the market, and we have to assure that your system is safe, and then they give the stars whether your system is capable of handling such difficult situations. And these are in Japan as well, and then US as well. So this is our parking system. We have ultrasonic sensors, camera and radar and front camera. So these are the mainly, but however, for parking, we only use ultrasonic and near range cameras, not radar. We have two main parking systems already in the market. One is the standard parking. Standard parking can offer surround view, full 360 degrees surround view and bird's eye view from the top. And remote parking, we can assure parking by autonomously in angled or parallel or perpendicular parking lines, and automatic emergency braking in case of parking time. If you detect some object, system will automatically brake, and reversing using a recorded path. That also one new feature we added. And then I will go into the other new features one by one in the next few slides. And then this is the premium sector. The premium sector, we even have memory parking. There is one application I want to highlight here. What is memory parking? And then and how we achieve that. And then trailer, the parking with the trailer is even difficult. So we are having the system how to park with the trailer and how the system could assist when with the trailer is attached to your vehicle. All right. So I'm skipping this slide. I already explained most of the part because autonomous parking, rear AB, and so on. And this is our sensor, main sensor for smart parking. This is ultrasonic sensor generation 3.1. So we can go up to 7-meter detection. And still the sensor is still ASIL-B safety level. Very low power consumption at the diameter of 50.5 millimeter, small sensors that is much suitable for the vehicle body mounting. So we have much accurate in this sensor we could achieve. Therefore, we can go for better high quality parking and advanced parking development with this. MOBIs has almost all the sensoric and then related circuitry that we could do. So we have the sensor and the processing IC as well, this MOBIs manufacturer, and then we know how to achieve because it's our own sensor, so we know how to get it into the software level and more quicker responses, and then we have the full control. So I will show you one video about the MOBIs autonomous parking, mainly how we do in the mainly the autonomous parking, memory parking assist, and then other parking. So first picture is memory parking, and then other image recognitions, how this system does. I will explain what is memory parking assist. Memory parking assist is the driver train your parking path. This is the training process. While the system is training the parking path, for example, in your house or in your home area or in your office area or anywhere. So you first train the system, that the system memorize this. And then after that, you don't need, actually, you can use the path to control the vehicle. You can hands-free and the vehicle itself goes and park. So that is called memory parking. So that involves mainly the ultrasonic sensor and the 360-degree field of view camera. There is only 2 sensors that we use. And then you can basically train the system for any sort of parking, parallel and diagonal and so on. And then you can get the car back as well with this same parking scenario. At the same time, you can detect the objects because it's autonomous parking, and at the same time, you can detect the object and then apply the emergency braking. Then we have image recognition, full image recognition around the vehicle. And then you detect the complete space. That is much more assisting, for example, in the narrow spaces and so on. And the full free space detection involved with that. So any parking scenario, the obstacles are detected for any form of obstacle. And then system fully autonomous, the parking function at the same time object detection. Another one is the ground view, because you can get the full top view around the vehicle by this camera. And then that is kind of an assisting function for the driver while parking. I will move into the, then I will go into the next step of how we achieve the memory parking analysis and how with this few number of sensors you could do this autonomous functionality. So the The theory behind this memory parking assist is visual SLAM. So we have 4 cameras around the vehicle. Then we feed these images into the neural network. With the neural network, we can find the key points. The neural network is not for object detection here, just to find the key points of these scene images coming from all these 4 camera streams. With this key point, if you have already trained the path, we can, with this key point, match with the already trained path. Your training process, you have these complete keyframes already in your memory, and then you have the 3D, 2D key points and 3D key points already saved in the map. In the while its operation, these images and the key points match with the already saved map and the key points. And then this is 2D mapping is not enough for the vehicle to control the vehicle. Then we transform that into the 3D world, this 2D matching into 3D world, and associate this 3D point association. And at the same time, once you have this association, then you know that you are in the right place, and then you converge that with the system to the right path. So that's how this complete system works. And then you need to triangulate this complete 3D vehicle positions and then path plan with respect to the trained path. The key part of this is the association of 3D points, because you could see that in the training process, you're starting one position, but in the application or control process, when you come back, you are not in the same position. But however, you could see the scene, and then with the associations of these 2D points to the 3D, with this visual SLAM and such, we could achieve that. This system can localize up to 10 centimeter, less than 10 centimeter, and up to 100-meter trajectories. So it is mainly for parking assist. So that means your home zone parking and parking in an office area or something if you have a dedicated parking spot. So you can train for that parking spot, and indoor and outdoor and both, and all weather conditions. That is the robustness challenge at night and the day and time and snow and so on, and trajectory or storage per location. So we can have multiple, at least at this system, we have 5 trajectories. We could save it in the system and we can recall in the controlling. So this autonomous parking, I mentioned that it's one application that we recently put into the market. Maximum training distance of 100 meters and maximum training speed is 30 kilometers per hour. And maximum control speed, when it controls, it's slow, 4 kilometers per hour due to the safety reasons. And then the standards provided by the authorities for autonomous parking. And coming into the next generation, what we are heading, actually, we try to put this product into more into the distance parking possibilities. For example, 450 meters, 300 meters, and 1 kilometer range that support for all sorts of parking applications. And then that is actually heading to valet parking. The valet parking is the park house dedicated for supporting valet parking. If the park house supported for valet parking, park house is sending the map. Actually, you don't need to train this case. The map is already provided to the vehicle via V2X communication channels. And then if the map is available, and then you can execute this autonomous functionality by your own. You don't need a driver in that case, because the park house will guide your vehicle to the free parking spots. So that has the ISO 23374 standards already, type 2. So we are following that for the next generation valet parking implementation. So we have all the ingredients right now. We have the memory parking assist that is trained, but if that is training because we need a map for the training, and however, if the map is provided, we can do the same automation with this. Then another functionality is the trailer assist function, how you park with the trailer. This doesn't involve much the sensoric. Actually, even normal vehicle sensors, we can do the job, like speed odometry sensors, acceleration and wheel angles, and other sensors, standard vehicle sensors. We can do the trailer reverse assist parking, but trailer memory parking is again the SLAM involved, that you need the camera, all 4 cameras. So I will show you a short video about what is the trailer reverse assist mean. So it is similar like memory parking assist. However, here with the trailer, you drive forward and then you train your forward path to the system, and the system memorize this trailer path, and then when it is reversing, you can have hand-free. This is already much interest in the most of the public. We get a lot of comments to need of this functionality, because always with the trailer, it's very difficult for parking. So this is the training process over. Then it memorized the path, and then in the reverse, it does the automatically. Okay, I will sum up. So I gave a full overview about the ADAS. I think you get a better understanding what is ADAS mean and some particular application that we developed recently. So we are continuously improving our systems and heading to autonomous driving. Autonomous driving needs more ingredients like autonomous parking and distance autonomous parking and more sensors and more software. So that's how we can achieve level 4 autonomous driving. Prediction is 2028 to 2023. Yeah, thank you. That's all from my side. Thanks all of you. So open for questions.
All right. Thank you, Mr. Thusitha. Yeah. So we are done with the two speakers. Thank you so much. I think it's very interesting to look at two different work coming from two different angles. One looking into the V2X and the other one from the intelligent transport system. Plus all the videos and so on that shows the actual working. I think we have some questions in the chat box. Let me just go through the first one. From Dr. David Cheng. This is my old colleague from University of Nottingham, Nimbau. I believe this one is for Dr. Ruzi. Dr. Ruzi, are you there?
Yes, yes.
Okay. So the first question from Dr. David Cheng, what is the application for remote driving?
Oh, okay. For the application for remote driving, as you can see just now, like smart parking is actually like it's a part of the remote driving. As long as the applications that require for autonomous vehicles, because the autonomous vehicles can only work with ADAS. Yeah. For instance, in order for the application to be autonomous, it requires for object detection, pedestrian detection, and the trajectory, the path trajectory, and for instance, in terms of how to drive for the vehicle to drive at a certain curve at the roundabout. So this one require more on the object detection, path trajectory. So these are all the applications that contribute to the remote driving. Okay, so these are the things actually. But of course, when it comes to remote driving, when we have all these applications, and the vehicle itself must have the capabilities like to handle the steering, to handle the brake, you know. So these are also the things in the vehicle itself, like the braking systems, to maneuver the steering. Okay, so all these are the applications that require to the remote driving. So there are a few applications involved actually. Okay. I hope that's answered the questions, yeah, Prof.
Okay, thank you. Hopefully, Dr. David, that answer your questions. Next question also for Dr. Ruzi from Prof. Madhya from AP Dr. Lim King Chuan. Any V2I use cases already implemented in Malaysia?
To be honest, not yet. Okay, if you wanted to see the real implementation, not yet, yeah, for V2I. But we do have cameras at the roadside or maybe at the traffic light, but then they are not really smart that can we implement the V2I. For instance, like to detect the pedestrian or maybe to detect the objects. Yeah, so our cameras are not that smart yet. They are there, but they are not smart yet. So once we have this AI expertise, so hopefully we can actually implement the V2I. Yeah, so we make all the images, the videos by using the AI to become smarter. But to answer the questions, not yet, but there are lots of research. Okay.
Okay, great. The third question, I think from Mr. Chen Yu Yang. How are latency and reliability defined in 3GPP requirements?
So basically, you can look at the details of the 3GPP requirements. The latency is more on from the source to the destination. Okay, they have actually specify the latency from the source to the destination. So from the vehicle to destination. So it's actually the latency measurement. So for the reliability, how reliable the communication is. So there is no drop happen during the transmission messages. So this is actually the reliability of the communications. Yeah, so there are no packet loss. So this is actually the reliability. So that's why it's very high to certain cases, 99.999, which only can be accommodated with 5G. But for the details, you can check the 3GPP requirements because different use cases have different latency and reliability. All right. Okay.
Okay, great, thank you, Dr. Ruzi. There is one question for Mr. Thusitha, also from Dr. David Cheng. Do you consider millimeter wave for the in-car and outside car detection?
I think this is related to the radar signals processing. Yes, so that is also in our discussion. That is in our area. Yes, the answer is yes for that.
So the answer is yes. That means you actually use millimeter wave as well in the consideration, is it?
Yeah.
Okay. All right. Thank you. Next question from Associate Professor Dr. Lim King Chuan. How would you see the market development for V2X with 802.11p versus cellular V2X? I think this one is for Dr. Ruzi. There are two questions there. So I think the first one is for Dr. Ruzi.
Okay, all right. So for the first one, yeah, 802.11p. Okay. As far as I know, it seems there is an interesting work who compared between 802.11p and cellular V2X. Yeah, but it seems that in terms of performance here, cellular V2X wins in term of lots of things. Yeah, like for long range communication, the cellular V2X outperforms than 802.11p. But when it comes to the vehicle communication, so that's why 802.11p is better. So I would really see that the market would go for the cellular V2X because of the performance, yeah, and because of the long range performance that it can support better performance than 802.11p. Okay, that's the answer actually. This is how I would see the market. Okay, all right.
Okay, all right. I think the second part is for Mr. Thusitha. Yeah, how many watts the MOBIs V-SLAM consuming during the training and the subsequent automated parking?
I understand this question. I mean, the one area is whether we repeat the driver repeats the training cycles. Actually, that is not happening. The driver can straight away train the path, and then you can use that path immediately. If the system doesn't find enough key points or any number of features around the vehicle, then system communicates with the driver. The path it's not successful in the training. Actually, it is not any issue with respect to consuming power and the repeated training is needed and so on. It's not. Actually, this complete VSLAM, I can tell you, this complete four processing cycle, 4-camera processing plus a complete algorithm is running in real time in a very small hardware. So you can imagine like 12 TOPS hardware, tera operations per second hardware, and then the complete cycle is the 30 millisecond range. We calculate complete thing, and then we give the results out. So in terms of the power, it's not at all an issue, but it is related. For example, for electric vehicles, is the power is matter. If you have more training cycles of this kind of systems, and it is very natural that you cannot do that. But we don't have any such issues in terms of training, how much power we use, and at the same time, computing we use very small hardware for the computation. Even normal air cooled, no very normal small hardware.
So basically, the amount of power that will be consumed will be quite small as well.
Quite small. It's not at all any
not really
significant.
significant.
Yeah.
Okay. All right. Thank you. I think Dr. David also say that thank you, Mr. Thusitha, a very interesting presentation. There's one more question. Chen Yu Yang, are there any field tests evaluating the performance of NRV2X mode 1 in coverage mode and mode 2 out of coverage mode? Are there any standards for the switch between the two modes? So I think this one is probably for Dr. Ruzi.
Okay, right. Okay, for the field test evaluating the performance, new radio. Okay, all right. I think because new radio use like millimeter wave, yeah. In Malaysia, it's gonna be 26 or 28 gigahertz. So in Malaysia, to be honest, it's quite difficult to have the field test unless Malaysia. I think they will have, yeah. Maybe there is a plan to have 5G new radio test bed, yeah. So if Malaysia, maybe there is I don't know, maybe there is a timeline for this. Of course, we need to have this. So once we have the test bed, so it's more likely, it's easy for the researchers in Malaysia to evaluate the performance for the new radio V2X mode 1. And for the mode 2 out of coverage, this is possible because there is a work in UITM, yeah, it's under Dr. Fazli. So they have done these buggies where these two other buggies, they have developed like autonomous buggies. Similar what, not similar, but they have the cameras, LiDAR, okay, they install in the buggies. And then these buggies, they can communicate each other through PC5. So they have done this vehicle to vehicle communications. So that is possible. Yeah, if you want to do practical, it's possible for that one, for the in coverage PC5. It's already done. But for the new radio, we need to have the test bed first, ready? And then that's possible. But I think it's in the plan, yeah, Prof. Yusuf, inshallah, because Malaysia is going to 5G new radio, yeah. So I hope, yeah, down the road before 2030, we might have that. Okay.
Yeah. Okay. I think that is the answer from Dr. Ruzi. Hopefully that answer your questions, Chen Yu Yang. Okay, let me have a look. I think we that's all the questions that we have in the chat box. If anyone from the audience would like to ask any questions, you can also raise your hand and switch on your mic. If we don't have any questions, there is a second question. Are there any standards for the switch between the two modes? Okay, sorry. I think that the Rosie didn't answer this question earlier.
Oh, okay. To switch the
Hmm.
mode, maybe you can refer to the TGPP standards. But as far as I know, to switch the modes, how it works is that when there is no coverage of cellular, there's no coverage, yeah, cellular coverage, then you can switch to the mode of B2V, yeah, PC5. So maybe once the technical code is published, yeah, maybe Prof. Yusuf, I will share with you, Prof. Yusuf, once it's published. So maybe you can escalate to the, IEEE members so they can have a look, because in that TC we specify what document. I can't remember because there are so many. Okay, but in the TC we specify which standard. Okay, all right. So maybe Prof. Yusuf, once it's published, you can share. I mean, you can share the website or the TC.
Yeah, actually, this is publicly available. Let me
Yes, yes.
share the link.
Yeah, but it's not yet.
Not yet. Yeah, I know
Yeah.
this one is not yet approved.
Yes.
Not yet published, but I think you can check on the technical codes, all the currently or the previously available codes in
Yeah,
the
maybe we can share the
uh,
link here. I
uh,
think so.
uh,
Yeah, we can share the link. So there are so many technical codes like IoT,
mm, mm,
smart cities, quite number of technical codes. Very
mm,
good if we as researchers we are aware of these technical codes, so that can actually drive us, yeah,
mm,
to
mm.
do the research work in parallel to the standards rather than our own mind, So that's a good thing.
Yeah, so I've shared the link in the chat box. If you want to have a look at the technical codes, it's open to public, so anyone can access it. So we have published a few technical standards before. I'm also part of this V2X, as well as previously we have published the crowdsource application, which is currently being revised as well.
Yeah,
So these are some of the current standards that we have been working on. Right.
yeah.
Okay.
Just to share, Prof. Yusuf, if let's say the researchers are interested to develop the ADA system or any V2X applications, they can refer to the 5G AA, 5G Automotive Association. They are white papers. Okay, they are white papers. They are also technical report. So you can check. There are so many, but they have different approach. They have categorized the V2X applications to I think 5 or 7, very different to 3GPP. But it's a very comprehensive. You can try to find 5GAA technical report or white papers. They have three versions. They have the first one about the spectrum, and then they have the details of the service requirements, service level requirements for each scenarios. But they have more. They have more scenarios than 3GPP. You can have a look. If you want to, research further, or maybe you want to propose new grants or new research proposal, you can have a look and check that 5DAA. That's a very good one. Okay.
Okay, all right. So if there is no more questions, maybe we can have a group photo. Can everybody switch on your camera? Hopefully we can have a group photo before we go. Dr. David, okay, Mr. Cheng Yu Yang has opened up his camera. Hi. The rest, Leon Chu, and anyone else? Yasita or Vira Kumara? No one is switching on their camera. Okay, all right. So we'll take a photo of whoever that we have at the moment. All right, ready, everyone? 1, 2. Okay, another one. 1, 2. There we can see Yasita there. Okay, so thank you everyone for coming. So we have come to the end of our session today. So this has been a great session. It's great pleasure to have both Dr. Ruzi and also Mr. Thusitha. I think the presentation was very helpful, very informative, and hopefully we can collaborate with each other on these particular topics. So thank you once again, everyone. For those who have not signed in their attendance, appreciate if you can fill up the registration form. Is in the chat box. Yeah. Okay. Have a good day, everyone,
Thank you.
and hope to see you soon.
Thank
Thank
you.
you. Bye
Have a nice
bye.
day. Bye bye.
Thank you, Mr. Tushita. Okay,
Bye
right, bye.
bye.
Bye,
Yeah.
bye. Thank
Bye.
you.